guys, so what we're doing today is 5.6. And as y'all have already heard, you can see on the note sheet, what we're looking at today is composite functions. And I believe most of y'all have worked with composite functions before, or at least in some way, shape, or form. Algebra 1, I think you've worked with them, or probably for the ACT class, for the ones that y'all that are taking it, y'all probably covered them as well. And what we're talking about, a composite function, is putting a function into another function. They are put together. Now, it doesn't look like the book is calling them this, but we call, or at least when I was in high school, we called them fog and goff. Because one way of writing a composite function, it's not listed here, is we say, if I'm using a little one, f is this here. This is one way to write a composite function. This f circled g, it looks like fog, F-O-G, or goff, g of f of x, or f of g of x. Because our g of f, or f of g of x, our fog, is talking about f of g of x. And goff is g of f of x. We're putting one function into another function. And when we do this, this is kind of the pictured form of it, is that we're taking the domain, the inputs of f. Well, apparently I'm going to scroll. One more time. There we go. And using it. So we're plugging the inputs into f of x and finding the output. And taking those outputs as the input of g and doing it again. So for our function f, we're taking the x values and finding the given y values. And we're taking those y values, plugging it into g to find the new value. We're going from one into the other. And for the first few problems, that's really just what we're going to find is f of g of x and then g of f of x. F of g of x is what we're going to find first. And I'm just rewriting it so it's a little bit bigger and we can kind of expound on this. I mentioned this last week, and it kind of made no sense when we were talking about f of x plus g of x, and I'm like, okay, we're plugging x into f of x. Because we're like, okay, that just gives us the exact same thing. That is what we're doing here. Because for all of these here, we're going to start inside and work our way out. And for this first one here, we're going to plug x into g of x. So that means I'm going to come up here for g of x and replace every x with x. Is that going to do anything? Well, no, it's just going to say that we have f of what? X squared plus 3. Because that's what g of x is. Any questions on this here? Okay, now we're going to do it again, but this time we're going to replace everywhere there's an x in f of x with x squared plus 3. So our first x here is now x squared plus 3. Then we have plus 2. So really I just replaced that one x with our s squared plus 3. Now it's good to put it in parentheses because here it really doesn't make a difference. Because do we have anything connected with the x? Do we have anything multiplied or squared or squared root? No. So having those parentheses here or not having them isn't a huge issue. But if we're talking about like the other one, we have x squared, we still need to apply that square to it. or if we have minus or a negative in front of it, we need to apply it to every part of what we're replacing x with. Well, for this here, we can really just drop those parentheses and combine like terms. 3 plus 2 is 5. So for us, f of g of x is x squared plus 5. And that's it. That's all we have to do for this composite function. Questions on this here? Let's go the other way. Let's find g of f of x. Because we found for these two functions here f of g of x, because f of g of x was our x squared plus 5. You don't have to rewrite that down. I'm just rewriting it down so we have it. Yeah, it should be the top of the next page. G of f of x. So this is what we're starting with. And again, I'm going to plug x into f of x, which really is not going to do a whole lot. Because really what we're saying, kind of a shorthand form, is I'm taking whatever f of x is equal to and just replacing it. So I'm just replacing f of x with x plus 2. So now we have g of x plus 2. Well, I know what g of x is. G of x is equal to x squared plus 3. But I don't have g of x anymore. I have g of x plus 2, yes? So that means everywhere in g of x where there's an x, here I need to replace it with x plus 2, because that's what I'm plugging into the function. So for us here, it's now not going to be x squared, it's going to be x plus 2 squared plus 3. Questions on this here? Well, we're going to have to simplify it. So that square, I'm going to have to actually multiply and simplify that out. Now again, it's very tempting to just say it's x squared plus 4, apply that square to both terms. But when we have this, it's just saying that we have x plus 2 times x plus 2. It's being multiplied by itself. And saying that it's x squared plus 4 is 2/3 right. We'd have the first and last term, but we would miss the middle term. And if we multiply this out, x times x is x squared. Then we'd have plus 2x plus 2x plus, because our x times x gives us x squared. The x times 2 gives us our 2x. 2 times x is the other 2x. And 2 times 2 gives us our 4. I would take a guess that some of y'all are starting to feel very comfortable with doing x plus 2 times x plus 2. And being able to see that this here is x squared plus 4x plus 4, yes? If you can see that and kind of work that way and do that well, this middle step of having the plus 2x, you don't have to write it out. Most of the time, I don't write out this part of it here, because I do the multiplications and add them in my head and keep it straight. Because if that you need to do that, do it. If you don't, don't. And the last part of this is just combining like terms. 2x plus 2x is plus, and this here is our g of f of x. So g of f of x is x squared plus 4x plus 7. Are these two composite functions the same thing? No. So for us here, g of f of x is not the same as f of g of x. There is a select few functions where f of g of x and g of f of x for two given functions are going to be the same. And the only time that they'll be the same, and we'll get into this especially in 5.7, is if they're inverses of each other. If they're inverses of each other, then they will be the same. These composites will be the same. But that's only a select group. Questions on this here? Let's look at the next one. So this time we have f of x is the cubed root of x plus 1. And g of x is 2x minus 4. So we want to find f of g of x. What is g of x for us? 2x minus. So we are taking g of x and replacing it with 2x minus 4. Because if we wanted to, we could have rewritten f of g of x and then wrote f of 2x minus 4. Or we can just start off with f of 2x minus 4. Because we went on and plugged x into g of x, or we're just replacing g of x with what it is equal to. And we get this here. Now we're told that the function f of x is equal to the cubed root of x plus 1. I don't just have f of x anymore, I have f of x minus 4. So that means for the function f of x, every place where there's an x is now going to be replaced with. So we'd have the cubed root of 2x minus 4 plus 1. Now, is there anything in front of our parentheses inside that cubed root? No, so we can drop them and combine our like terms, which would be the negative 4 and 1, yes? So it'll tell me that I have the cubed root of 2x minus 3. And this is our f of g of x. Now, we would want to simplify it if we can. Is there any way that I could factor 2x minus 3 so that we get an expression to the third power? Well, no. What's the degree already? 1, right? If the degree is 1, we can't factor this at all. And I can't just magically add terms. So that's as far as it goes. Questions on this here? We ready for the next one? It's actually a little bit easier than this. Bless you. So this one here, we have g of f of x. So I mean, as I said in the last one, we could rewrite it as g of f of x and then input x into f of x, or just start off by saying g of the cubed root of x plus 1. Well, we know that g of x is 2x minus 4, but we don't have g of x anymore. We have g of the cubed root of x plus 1. So I'm going to replace every x with the cubed root of x plus 1. Yes? So I'd have 2 parentheses cubed root of x plus 1, close parentheses, minus 4. Okay, so we have 2 times our cubed root, which would be what? Well, 2 cubed root of That's actually it, because we're multiplying 2 by the cubed root. So we have 2 times the cubed root of x plus 1 minus 4. Now the only way we would apply the 2 inside the cubed root is if we were multiplying our cubed root by the cubed root of 2. Because when we have the roots the exact same, we can multiply what's inside. But that's it. That's all we have to do for this here. Questions on any of this here? A lot of this coming back to us for doing these composite functions. Do we need to do another one of these, finding these composites, or do you feel comfortable with these here? We feel pretty comfortable? Because I feel like y'all are comfortable with this here. I'm just going to do one more just so that we see this here. This is a little bit, just little, itty bitty difference. Because up to this point, we really haven't had to distribute too much. A little bit with our first one where we had to square, but let's go on and see this so we can at least have seen it again. You've seen it before. So for this one here, we have g of f of x. Well, f of x is our 2x plus 7. So we replace f of x with 2x plus 7. Now we're going to plug 2x plus 7 into every x in g of x, which would tell us that we have 3 parentheses 2x plus 7 plus 5. Well, we need to distribute the 3. 3 times our 2x's plus 21 plus 5, which tells us that we have 6x plus 26. Nope, that's it. Because we've got it already distributed. Yeah, it's already as simplified as it gets. Because since 6x and 26 are not like terms, we can't add them or combine them. There is a greatest common factor between 6x and 26, which would be 2, because 3 doesn't work, so 2. But rewriting it as 2 times plus 13 isn't really any simpler than 6x plus 26. So we'll leave that alone. That might be helpful if we're trying to solve, because it gives us a little bit reduced form of the same function. Because the solutions really for 3x plus 13 and 6x plus 26 would be the exact same. The rest of the function would look a little bit different. It would have a greater slope for our 6x plus 26 than 3x plus 13, but it would still cross the x-axis at the same spot. So here we don't have to worry about greatest common factor. Any other questions on this here? All right. Evaluating composite functions. Now, with addition, subtraction, multiplication, division, when we evaluated those functions for a given value, well, the first thing we did was find it, because we found out what f plus g of x was and then plugged it into that one. And the same was true for addition, subtraction, multiplication, all of those 4. Here, we're not going to do that. Because for one, that's just tedious, especially for trying to find 3, yes? And again, as I said at the start of this lesson, all these here, we're working from the inside out, yes? So for this one here, we're looking at f of g of 3, yes? Well, our g of x function is x squared plus 2, yes? And what are we wanting to plug into it? So f of 3 squared plus this looks like it's about to get really kind of massive and big. I mean, if we left it in this form here of 3 squared plus 2, yes, it could get massive, especially if we plugged it into f of x at this point here. I don't see the point of doing that. Because 3 squared plus 2 is just a number, yes? Let's simplify it. We can plug it into a calculator. 11, because 3 squared is 9, plus 2 is 11. Okay, now we have f of 11. So we'll do the same thing, except plugging 11 into f of x, giving us 3 times 11 minus 4. Three times 11 is minus 4. So f of g of 3 is 29. And that's it. And again, all we did was work from the inside out. I kind of like these. I think it's on the test. I know it's on the, might be on the test. I know it's on the review sheet. One of these here that I will have y'all do is going to be f of g of 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 like 3. But all you're doing is essentially that same thing just 4 or 5 times over. Because here we did it twice, so it's just adding f of g. It's using the function over and over and over again. But really, that's it. Let's look at one more of these, because these I think y'all find nice. So, g of f of negative 1. So, f of negative 1, we're going to plug negative 1 into the function f of x, which would give us 3 times negative 1 minus well, 3 times negative 1 is negative 3, minus 4 is, now we're going to find g of negative 7, which would be negative 7 squared plus negative 7 squared plus 2 is 51. So, because our negative 7 squared is going to give us a positive 49, plus 2 gives us 51. So g of f of negative 1 is 51. That's it. Any other questions on this here? How do we feel about this? We feel good? We need another example of one of these. No, because because again, I add more examples in here just in case we need them. If y'all are understanding this, doing a lot more examples is not going to make the concept any more clearer. Because I think there's those two, same thing. And I don't think this is in your packet. It may not be. Yes, it is. Okay. I'm gonna work this through with y'all. We'll do these first two. I don't put a big emphasis on this, the domain and range. And college algebra might come back over this and have y'all do this. I don't see this pop up much, especially on the ACT. What this is talking about is the domain of these functions. What are the x values that we can plug in? And for a composite function, get a blank sheet of paper, we have our x values. And our function f of x, or x, takes us from the domain to the range. And for a composite function, what we're doing is we're taking the values from that range, g of x, and applying it to its range. So this here is g of f of x. So if there's any restrictions that are applied here or here, have to be taken into account. Confusing yet? A little bit. Let's look at an actual problem so that this makes a little more sense. For us here, f of x equals x to the negative 1. Well, we don't normally leave a negative exponent because we would move it from the numerator to the denominator. Okay. Here, x cannot be what? 0. Because here, if x is 0, we have a division of 0. That doesn't work. So, we're looking at the function f of g of x, yes? So let's actually get that kind of picture back up. Because we have our x values going to our y values for g of x. Because if we're working from the inside out, we start with g of x, plugging x into g of x to get the range. And from here, we then apply f of x to get its final range. Because it's taking this, f of x is treating this as its domain. Yes? Now we just said x cannot be 0 for f of x, yes? But our starting point for the domain is here, yes? So we need to see what value would give me 0 for the range of g of x. So it's really looking back to this here. What's going to make this 0? So what we can do is set 2x minus 4 equal to 0 and solve. So we'd add 4, saying 2x is equal to 4, and exactly x is equal to 2. So if 2 is contained in the domain of g of x, it would give us an output of 0, which would give us an undefined value in f of x, yes? So the domain for this here is going to be all real numbers except and this is a shorthand kind of way to write it. Because it's all real numbers excluding this set. And it's the set containing 2. All other numbers work, but because 2 would give us a value of 0 coming out of g of x, working our way out, we can't have that because it'd make it undefined in f of x. So it's almost, we've got to work our way inside out looking at restrictions. Well, this one here, again, our f of x function is just 1 over x, and we said x cannot be 0, yes? F of x, and then we have our g of x to get to the final range. Y, x. But we're applying f of x first, yes? So that means in this first one, well, we can say x cannot be 0, yes? That's the only one that has restrictions. It means I don't have to worry about anything else. Because that not being 0 means everything else works. It's going to go, all the other values are going to go to y, and all of those are going to go to the final answer. So here, the domain is all real numbers except 1, 0. So that one's a little bit nicer, especially when the restrictions are applied to the function that's being done first. It makes it a little bit easier to see what they are. Because a lot of the times when we find our composite function, it makes it a little bit more interesting. And this, well, I say that. Let me look again. Because watch it still be 2. Because 2, no, it's just 0. Erase this. Because when we look at this here, g of, well, f of x is 1 over x. And if we apply it, 2 times 1 over x minus 4 will give us 2 over x minus 4. G of f, well, x can still not be 0. That's our only restriction. Because here it's not too bad, but there's sometimes with these composite functions that for some reason the variable can sometimes eliminate out, or some of the restrictions that we did have simplify out or removed. Because if we look at, say, the function g, you don't have to write this down, is equal to the square root of x minus 4. And f of x is x squared plus 4. If I plug it in, we'll have the square root of x squared plus 4 minus 4. Plus 4 minus 4, gone. Square root and x squared give us just x. But the restrictions on g of x are still there. The restrictions on are there, and we still have to take them into account. So there's some of these that when we look at the restrictions on domain and range still come into play. But I don't put a big emphasis on domain and range. It's mainly just finding the composites. That's it. So your assignment is on page 281. Five through 12. So 5 through 8, you're finding f of g of x, g of f of x, and just figuring out what the function is like we did at the start. There are 2 we didn't, quote unquote, didn't cover. G of x and f of x. You're just plugging the function into itself instead of doing f of g of x or g of f of x. Same thing, it's just doing the same function twice. Then 9 through 12 is finding the value. So they'll give you f of g of 2 or f of g of negative 3, and you're just finding those values. 25 through 28, find the composite function and state the domain. Just find the composite function. I don't want the domain for those there. And the main difference for those is you're going to have 2x to the negative 1 and 5x minus 5. Oh. It's not annoying at all. For those there, for 25, 26, you don't have to rewrite x as if you have a negative exponent, you don't have to put it to the denominator. You can leave it as a negative exponent. I'll take those for that. even though it's against the simplification rules, I'll go on and take that if there's still a negative exponent. Okay, so 2 of those, you can have negative, or x to the negative 1 in your answer. I'm not going to make you rewrite it as I did for the one example I threw up there, 2 over x. You could leave it as 2 times x to the negative 1 and the rest of it, okay?